Alright, this is the 2013 exam. Question number 1. This is the old format of the exam, which means there's 6 FRQs on these things, and they were all long FRQs. They were all supposed to take you 15 minutes. You won't ever see number 4 in here because number 4 is strictly a net ionic equation problem in these as we go through the older exams, but this is a fantastic little KSP FRQ, so we're going to work through it. It's the kind I like. There's a lot of workout stuff and not a lot of me writing explanation stuff, so I like when it's easy to tell whether the answers are right or wrong. So anyway, here we go. It says answer the following questions about solubility of some fluoride salts of alkaline earth metals. And so 1A says a student prepares 100 milliliters of a saturated solution of magnesium fluoride by adding 0.5 grams of magnesium fluoride to 100 mils and stirring until no more solid dissolves. Assume the volume of the magnesium fluoride doesn't do anything. It determines that the concentration of fluoride in the solution when it dissolves is 2.4 times 10 to the negative third molarity. That'll be important. So 1A, part 1, says write the chemical equation for the dissolving of magnesium fluoride. This is just a little dissociation equation. We have magnesium fluoride. That guy is going to dissociate into magnesium ions and into, don't forget the two fluoride ions. So it looks just like that. That's the balanced net ionic equation. You get a point for that thing. Then part 2 says calculate the number of moles of magnesium fluoride that dissolved. What I know is the molarity of the fluoride ions. So I know that 2.4 times 10 to the negative third moles of fluoride dissolved per 1 liter. And then I'm converting units like a crazy human here. So what I want to find is the number of moles of magnesium fluoride that dissolved. So first thing I did is got rid of the liters. That's per 1 liter. I didn't have 1 liter. I had 100 milliliters of the saturated solution. So I have 0.1 liters, and so I multiply that guy by the 0.1, and that gives me 2.4 times 10 to the negative fourth moles of fluoride ions. I want moles of magnesium fluoride that dissolve. So I'm going to go from moles of fluoride ions, I'm going to go moles of fluoride to moles of magnesium fluoride. And that is the 2 moles of this to the 1 mole of that. And so after all my units go away, I'm just left with moles of magnesium fluoride, and I get 1.2 times 10 to the negative fourth moles of MgF2 that dissolved. That's part 2 of A. Hopefully you can see it all there. Then part 3 of A says determine the value of KSP for magnesium fluoride at 25 degrees Celsius. So I need to come back and do KSP. The KSP is going to be equal to the concentration of magnesium ions times the concentration of the fluoride ions squared. Don't forget to square it, right? This is products over reactants raised to their coefficient. So that fluoride there has got to be squared. And then I get to plug in what I know. I know the fluoride ion concentration from the beginning of this thing. So KSP is going to equal the fluoride ion concentration they fed me early on in this thing. They fed me this 2.4 times 10 to the negative third in the question. And so what's magnesium going to be? Magnesium is going to be half that much. And so we're going to have 1.2 times 10 to the negative third here for that concentration, and 2.4 times 10 to the negative third there. Don't forget to square it. It's just keeping track of a few numbers there. And then we can solve for our KSP value there. We plug that guy in the calculator, and the KSP is 6.91 times 10 to the negative 9th, I believe. There's part 3. So what do we got? Point breakdown in part A. We get 1 point for the balanced equation. You get 2 points here. You get 1 for, it says the correct calculation of moles from the concentration, and then 1 point for the stoichiometry. So you get 1 point for eliminating the liters unit. You get 1 point for the 2-to-1 ratio. There's 2 points there, and then in part 3 there's 3 points. You get a correct value of the magnesium ion concentration as a point for the right setup of KSP, and then a point for your KSP value at the end. There's 3 points in that, so we're up to 6 points already. And now we're ready for part B. So part B says a beaker contains 500 milliliters of a solution in which calcium and barium are present at this concentration of 0.1 molar. The student intends to separate the ions by adding some fluoride, solution 1 drop at a time, from a burette. It gives us the KSP of the calcium fluoride and the KSP for the barium fluoride, and says which salt will precipitate first. Justify your answer. You could go through and figure out how much fluoride, and the least of the amount of fluoride that you'd have to add would come back and tell us which one precipitated first. But we have the KSP values for both of these, and they're going to break into the same number of ions for these dissociation equations. And so if we look at those KSPs, that KSP says this value lies farther to the left, which means it will turn into solid, that solid reactant, first, because it has a smaller KSP. So calcium fluoride is going to precipitate first, and this is how they explained it as well. They did it conceptual. They didn't do it with a calculation. They said calcium fluoride will precipitate first because the smaller KSP value indicates less dissolved salt. That's it. That's part B, number 1. Which salt will precipitate first? The calcium fluoride. Part B2 says assume that the addition of sodium fluoride does not affect the total volume. That's nice. No air resistance. It says calculate the minimum concentration of fluoride necessary to initiate precipitation of the salt selected in part B1. So they want to figure out what is the concentration of fluoride that's necessary. So we've got to set up a KSP here. The KSP for the calcium fluoride is going to be the calcium ions times the fluoride ions squared. They gave us the KSP for calcium fluoride in the problem. 3.5 times 10 to the negative 11th. So we have 3.5 times 10 to the negative 11th equals, we know the calcium ion concentration because they told us the calcium and barium were present at a concentration of 0.1 molar, and so we know the molarity of this is 0.1 molar, and they want to know what is the concentration of that fluoride ion. Don't forget that it's squared there. That squared gonna haunt some people. And so we plug that in and we solve for X. And when we do define X, the fluoride concentration here is going to equal 1.87 times 10 to the negative 5th. That's in molarities. That's part 2. One point for B1, 1 point for B2. And then we're to part 3 on B. Part 3 on B says calculate the minimum volume of 0.2 molar NaF that must be added to the beaker to initiate the precipitation of the salt selected in part B1. So we now know the concentration of the fluoride that's necessary In B2, this is the concentration that we want to get. We know what the volume was of that entire solution that was there because they told us this beaker contains 500 milliliters. Good. So this becomes an MV equals MV. We want to figure out how many drops of that 0.2 molar sodium fluoride do we have to put in to get this 500 mils of this concentration of fluoride. So it becomes an MV equals MV problem. Where we've got the initial molarity of the fluoride, 0.20 molar, times the volume we need to figure out how much we need to add of that. That's equal to the concentration of the fluoride we need here, 1.87 times 10 to the negative fifth. That's how much molarity we need, times the volume of that solution. That was 500 milliliters, and you can leave it in milliliters. They don't ask in that particular question for it in liters or milliliters, but it's going to be small enough in milliliters that I would leave it in milliliters. The volume that's necessary there ends up being 0.047 milliliters. Not very much to get that concentration. Good. It's a nice tiny little burette that's dropping out of, pretty accurate. And then we got one more. Part C says there are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate that's formed in B. My kids did well with this question, and when we go back over it every year, they do well with this question. If you got some solid and you want to dissolve more solid, the easiest thing to do is to add more water. If you add more water, more stuff will dissolve. How else can you get more stuff to dissolve? Lots of times you could heat the solution. Heating the solution sometimes helps. Those two you should be pretty comfortable with. The third one, and this is one that I use for qualitative analysis lab, is lots of times when you can't get something to dissolve when you heat the solution, if you add some acid to that solution, you can get things that normally don't dissolve to dissolve. It only wanted one of those in part C. It says one procedure to redissolve precipitate. Those three are good. And so in qual lab, lots of times I'm not only heating the solution, but I'm adding a little bit of concentrated nitric acid, and that will help to dissolve things that normally wouldn't dissolve. So there you go, 1 point for that, and there's your 10 points on 2013 number 1. Great little question with KSP for us.